Hi guys, let's try to derive magnetic field of a bar magnet at an axial point. So try to get the mathematical expression for magnetic field strength due to a bar magnet at an axial point. Suppose this, if I take a bar magnet, so suppose this is NS, this is north pole, and here you can take north pole, unit north pole, and this is south pole, and this is magnetic axis. So both poles are separated by a distance of 2L. Suppose at middle, if I can take this as L, and from here to here again L, the total length equal to 2L. Suppose if I consider a point along its axis, we need to find along axial line. Suppose if I consider a point P along the magnetic axis. So this is a point location P. We need to find the magnetic force at here. So just imagine that some another magnetic material might be kept at here. So we need to find what is the force on that. Suppose if I see clearly from north pole to the point P, suppose if I take this as at a distance of, from center we can take, we need to take from center, not, so from center of magnet the point P is at a distance of R, the location of point P which is at a distance of R. So from north pole its distance from changes to, it is R minus L from north pole, but when it comes to south pole it becomes long distance. From south pole the distance becomes R plus L. So try to get it this difference in the distance, because we consider the point from the center of the magnet. Now we need to find from the each poles, not from the center, we need to find from the each poles. So that's why there is a change in the length from the two poles. Now not only that, here we need to show the directions. Suppose at P the force due to north pole, it is in this direction, and from the south the force is in the opposite direction. No, it is in the opposite direction. Or otherwise this you can understand, you keep another north pole of a magnet for a moment to understand that. So north and north, what happens, they repel each other. So this is the force due to north pole along in this direction, and exactly the south pole acts opposite, that is the force due to the south pole at that point P. Now we define a unit north pole. So that unit north pole placed at point P. So that is the consideration, you can take it. Suppose a unit north pole placed at point P, at location P. So if it's no unit north pole, so the north pole and north pole of the bar magnet, so they repel each other, and the south pole and south pole of the bar magnet, they will attract each other. I think now you got that meaning. Yeah, let's go ahead. Now if I use Coulomb's law of magnetism, force F equal to mu naught upon 4 pi times Q m1 and Qm2 upon r square. Okay, if Qm is the magnetic pole strength of the bar magnet, if magnetic pole strength of a bar magnet equal to Q suffix m and its length, magnetic length, equal to QL. Now here at point P we placed a unit north pole. It means its value I supposed to take as 1. Now if I write that force due to north pole at P equal to mu naught upon 4 pi times 1 Q suffix m is the magnetic pole strength of north pole of a bar magnet times 1 is the unit north pole which is placed at point P upon the distance square. So here the distance square equal to r minus L whole square. So that is the magnitude of the force. And if you can write the direction is along, I can represent that as N2P direction, north pole of bar magnet to the point P in the same direction. So here the character, these two characters are very important. So 1 Qm is the magnetic pole strength of a bar magnet of north pole, and 1 is the unit north pole what we place at here. Its magnitude equal to 1. That's the reason it becomes as like that. Now if I drop the 1 at here to write as a clear, F suffix n equal to mu naught upon 4 pi times Qm upon r minus L whole square. Direction, same direction, along N2P. Similarly, you can write the expression for magnetic force. Magnetic force exerted by south pole. So here I forgot to write magnetic force due to north pole on unit north pole. Try to get the difference between these two terms, north pole and unit north pole. Here the north pole, precisely here it is north pole of a bar magnet, on unit north pole. Now this time I will write the clear at here. Now the magnetic force due to south pole of a bar magnet on unit north pole. Unit north pole at point P. So this time we need to consider these two terms, south pole of a bar magnet and which is experiencing a force on a unit north pole. So if you can write the same Coulomb's law expression, the F suffix south, this time the force due to south pole equal to mu naught upon 4 pi times Q suffix m is the magnetic pole strength of south pole times 1, here 1 is unit north pole, upon distance square. Now this time the distance r plus L whole square, because if you can see the diagram carefully, the one more r is added at here. R is the distance from center to the point P, and L is the extra distance from the center to south pole. So that becomes R plus L whole square. Now if you write the direction, now the direction is along, now it is north, south and north, they start attract. Now the direction is from P to S, attraction force, that is from P to S. Here the directions are important because the directions are vectors. When it comes to addition of vectors, we need to add by considering their directions. So don't neglect about directions. Suppose if I drop 1 in the above expression, mu naught upon 4 pi, I would like to write clear. So it's the Qm upon R plus L whole square. So let me call this equation 1, and this is along from P to S direction. This is equation 2. Now at the same point we got the two different forces, and that the two forces also opposite in direction. One is, if you take, one is acting along east direction, another one is acting along west direction. To get the net force, so we need to sum up these two forces. Therefore the strength of the magnetic field at point P is, so that is the magnetic field due to axial. The magnetic field due to axial equal to, that is the force, the net force experienced by, this is the net force experienced by, net force experienced by unit north pole. So here the unit north pole helps us to find what is the net force. Now to calculate the net force, just these two are the two vectors. We need to subtract them vectorially, or we can use the head and tail method to get the net, but here I can do that directly. The magnetic due to axial, so one is along in this direction, one is along opposite direction, so we can add vectorially. We need to subtract each other, so the subtraction goes to the force due to north minus the force due to south, so Fn minus Fs. So if you can write that, mu naught upon 4 pi times Q suffix m upon, it's R minus L whole square, minus mu naught upon 4 pi times Qm upon R plus L whole square. So we shall do further simplification at here. Try to get the common factor. Therefore B axial magnetic field due to axial equal to, you can pull the common factors. Mu naught upon 4 pi is common. Not only that, here I can get the common of the Q suffix m also, and here remaining terms are 1 minus 1 upon R minus L whole square minus of 1 minus R plus L whole square. Yeah, here we can do the LCM, and I am leaving that exercise to you. I will directly end up with the writing by writing the final expression. Magnetic field due to axial equal to mu naught Qm upon 4 pi times. So if you can do the LCM, we can get that to 4RL upon R square minus L square whole square. Yeah, like this kind of derivation we already did for electric dipoles. The same results we got it at there also and here also. And I would like to do some little modification at here. Suppose you don't cut the 4 and all, so because we can use that in different way. If I can divide this mu naught times 2Qm times L times 2R. So it means I divided the 4 like this upon 4 pi times r square minus l square whole square. Since this is B axial, since we need to write that expression in terms of magnetic moment M equal to the product of magnetic pole strength times the length of the magnet. So this we can insert in the expression. Here M is magnetic moment. So here we cannot define that magnetic pole strength as but we can define the strength of a magnet in terms of magnetic moment. So that's the reason we try to change the expression B axial equal to mu naught upon little m times 2r upon 4 pi times r square minus l square whole square. Now this is the expression for the magnetic field at a point P, the strength of the magnetic field at a point P. For a moment, if you take, if the point for a short bar magnet, that's the condition for short bar magnet. This is another condition, or we can take as a note for a short bar magnet. So if you can take that the length is very much smaller than the distance of point R what we consider. So we have taken a bar magnet like this, and we have considered this is the length and L, and we have taken a point R which is far away, and this point is very far. Then we can neglect the L at here. Now you can drop L in the denominator and write the remaining expression. So in this case, neglect L in denominator. Therefore magnetic field due to axial position equal to, for a small bar magnet, which equal to mu naught upon 2mr upon 4 pi times, here I can get, if I drop L at there, I can get r power 4, and you can cut 1 r and in r power 4. So we can end up the remaining expression equal to mu naught times 2m upon 4 pi times r cube. So don't cut the 2 and 4 at here, let it be, it's easy to understand also. So now we need to find out the direction. The direction is, if you can subtract two vectors from that like this, you need to flip the vectors. I think you can get it at here. So if one vector is east direction and another vector is opposite direction, what we do usually, we can flip one of the vector, and it means if one vector is in this direction and another vector is in this direction, so we will flip this another vector into the same direction, then we can get the resultant. So this is how we do A minus B. Suppose if A and this is B, so the B became minus B at here, the black vector. Now they both are showing the same direction. Now in this case they both are showing the east direction. If east, you can take in this direction. Then at here it is showing, both are showing towards the N2P. So the resultant vector direction is, the resultant force direction is along N2P. I hope you got that meaning. So this is the final expression what we want, that the magnitude of the magnetic field at a point, at an axial point, and its direction. So from this we got clearly the magnetic field at any axial point of magnetic dipole is in the same direction as that of its magnetic dipole moment. So as per I said, magnetic dipole moment direction from the south to north pole. So here I can write that the magnetic field at any axial point of a magnetic dipole is in the same direction as that of its magnetic dipole moment. So magnetic dipole moment direction, you just remember that the magnetic dipole moment direction is always from south to north. This is the magnetic dipole moment direction. So in the axial position, always the magnetic field direction is in the same direction of magnetic dipole moment direction. So let us discuss one more case. What about if you take a point at an equatorial point? So the magnetic field of a bar magnet at an equatorial point or if you can say that a point which is perpendicular to the magnetic axis. So for that, as usual, let you consider a bar magnet. Suppose this is a bar magnet. So to this bar magnet, let it be south pole and here it is north pole. So this is north and this is south. They both are separated by a distance of 2L. So from the center, if you can take this as, suppose this is center. So this is length L and this will becomes length L from the center. Now if you consider a point P, that is exactly at here, a point P, which is a distance of x from the each pole. Now from this pole to this distance equal to x, and likely if you can take from this pole to this distance is also equal to x. Now this is the distance, the P from the center. Here you can take this as R. Now if this distance equal to x, and we can use the Pythagoras theorem to find the value of x, that we can do later. So let it be magnetic axis, what I draw right now. So let me make color, so it will be little attractive to get the things better. Okay. Now let me write down for a moment the x value equal to under root of r square plus l square, that we already know it. The same thing at here also, x equal to under root of r square plus l square. And when it comes to at point P, we need to mind about force. The force is along in this direction, one force. Since we will keep a unit north pole in the same direction. At point P, we place a unit north pole. As like earlier, at point P, place a unit north pole. So unit north pole at point P is repelled with the north pole of bar magnet, so there is the resultant direction, but it will attract to the south pole of the bar magnet, so this will be in this direction, and we will get the resultant direction, so the resultant direction along in this direction. So this will be the resultant of these two forces. So I can write this as F R, this resultant force as F as R, and this resultant force will make an angle theta, that we got it. So that angles thetas will be same angles at here with the magnetic axis. So if you can remember the same kind of diagram we already draw for the electric dipole at an equatorial point. Yeah, situation is same. There we have taken the help of the unit positive charge to derive the expression. So, but at here we have taken that unit north pole. Now to find the magnitude of the force, we need to write the expression for force due to north pole equal to mu naught upon 4 pi times, if Qm is magnetic pole strength of bar magnet of north pole, and 1 is the unit north pole magnitude upon the distance at here. I can write the distance as x square. So this is from the Coulomb's law of magnetism. If you can write this direction along, the both are repelling along N2P. And likely if you can write that expression for force due to the south pole equal to mu naught upon 4 pi times Qm, it's the magnetic pole strength of south pole upon 1, that is the magnetic strength of the unit north pole upon distance square equal to x square. Now its direction is along P to S, because these two poles are attracting. Now to get the net force, so here you can use any law, triangle law or the parallelogram law to get the resultant force. Now to get the resultant force, there the resolving of components, so I don't draw that, so I will draw it here. If this is one of the force, let me take the help of this coordinate system. So if this is the coordinate system, yeah, we know this, but one small little explanation. Yeah, if this is one force, this is force due to north, and it resolves into two components. If it is theta, it resolves into two components, horizontal component and vertical component. And this is the one more force which is also resolves into two components, horizontal component and vertical component. Now the vertical components which acts on the both directions, which I am going to draw with this bold color. So these vertical components are equal in magnitude and opposite in direction, so they get cancel each other. Okay, but the horizontal components, if you can draw with these thick lines at here. Oops. So now the horizontal components which they act along in the same direction because of the both. So in the both cases they both are acting in the same direction, they will be add up. So in this case we need to mind about theta according to direction. The thetas are, I think this is goes to theta on both the direction. Now the two components of f cos theta, fn cos theta and f south cos theta, these two will be add up, and fn sin theta component and f due to south sin theta components, they will be cancelled out. So these two are equal and opposite and they will cancel out. And finally we can get that net magnetic field at point P. So that's the net magnetic field. Yeah, theta is along in the horizontal direction. Now we can get the net magnetic field, that is the resultant. So the resultant magnetic field, the net magnetic field at point P, yeah, at an equatorial point P is, so that is B equatorial is equal to net force on unit north pole, net force on unit north pole, unit north pole placed at P. Placed at P. So this is our helping hand, my dears. Unit north pole. From where did I bring? Don't ask that one. So it is just for helping hand. So let us finish this. B equatorial equal to net force. I can get the force Fn cos theta plus Fs cos theta. So what is the magnitude of the force? There we got that magnitude of the force due to north pole, Fn equal to mu naught upon 4 pi times Qm by x square, mu naught upon 4 pi times Qm upon x square cos theta. Now south also same, mu naught upon 4 pi times Qm upon x square sin theta. Sorry, it's also cos theta. Then we can add up simply. So it's cos theta. So 2 times you can get 2 times mu naught upon 4 pi Qm upon x square cos theta. Yeah, substitute the value of x at here. So this is magnitude of big equatorial. So before that, let me get the value of cos theta at here. So 2 mu naught upon 4 pi times Qm upon x square. What is the value of cos theta? We got it at here. So you can take any right triangle in the figure. If we take this as at O, then easy to get one right triangle. So from right triangle O N P, so hypotenuse is x and base is L and perpendicular equal to R. Can get the value of cos theta. Cos theta equal to L upon x. And we already know that x value at here, x equal to, that I can write it separately, and x we already got from the same triangle. X also we can get it at x equal to under root of r square plus L square. So I can substitute the two values at here. From cos theta equal to L upon x, L upon x. Yeah, magnetic B equatorial equal to mu naught upon 4 pi times 2 Qm times L upon x cube. Now here we know that 2 Qml equal to magnetic moment. It's always follows us. Magnetic moment. So finally, let us change it into a memorable equation. So B equatorial equal to mu naught upon 4 pi times, it's second right, that's a little m upon x value equal to, I think, r square plus, it's r square plus L square whole upon 3 by 2. Yeah, here cube is there, and under root you can get it there. So everything together you can write there. So here M is very important character, my dears. So M equal to magnetic moment. Magnetic moment, just like dipole moment. And let us use a condition. The condition is for a short magnet. For short magnet, that equal to that L is very much less than R. The distance is comparatively neglect. Now finally this expression will be changes. Magnetic field due to equatorial equal to mu naught upon 4 pi times. If we neglect L in the denominator, so I write it here, neglect L in denominator. Therefore mu naught upon 4 pi times M upon its R square whole power 3 by 2. So you can cut the 2 and 2 at here. So magnetic field due to equatorial, be equatorial. Don't be boring, just practice with this. Mu naught upon 4 pi times M upon R cube. Now what about direction? So I did not mention anywhere in the direction. You can see the direction this time. So I think so this time it is flipping towards to P to R. Yeah, here I have taken a 1 point R. So this direction is along P to R you mention. Or if you comfortable with especially unit vectors, you can mention along the unit vectors also, or negative y axis or negative j axis. Anyway, here I noticed a character at there, so we can mention that the equatorial direction. So the direction of magnetic field equal to along P to R direction. Now what it means to say, the magnetic field at any equatorial point of a magnetic dipole is in the direction opposite to its magnetic dipole moment. Always we are linking with magnetic dipole moment. So if we can take magnetic dipole moment as a standard, whatever we express that we will represent, or we can make a comparative study to that. So that's easy to understand also. So in this case we can say that the magnetic field at any equatorial point of a magnetic dipole is in the direction opposite to its magnetic moment direction. Yeah, since we got the magnetic moment direction as a standard, that magnetic moment direction is always from south to north pole of bar magnet. Not only bar magnet, any magnet. The magnetic moment direction is always directed towards from south pole to north pole. So with this parameter we are explaining about the magnetic field direction at any equatorial point is in the opposite direction. Is in the opposite direction to the magnetic moment direction. But when it comes to equatorial point, I think you remember that equatorial point always gives along in the same direction. The magnetic field at any axial point, sorry, not an axial point, sorry. mess up. The magnetic field at any axial point of a magnetic dipole is in the same direction as that of its magnetic dipole moment. If it is the axial point, so it is in the same direction of the magnetic dipole moment. But when it comes to equatorial point, it is opposite to the direction of magnetic moment. So these two gives the expression for the strength of the magnetic field due to because of a bar magnet, and the direction we compare to the magnetic moment. So here among this character is very important, which is known as magnetic moment. The product of magnetic field strength and its magnetic length we define as magnetic moment.